Hello everyone. In the second part of the lectures on inferential statistics, we will generalize the two-sample t-test, the unpaired two-sample t-test, to what is known as the one-way analysis of variance. Okay, and so by doing that, we will introduce the concept of factors. And so in two-way ANOVA, I hope to show you that knowing all the factors that could impact or influence your conclusions is very important. And as promised, we will finish with a more deeper look at power analysis. So before we start, I'm going to execute this code here so that we can run the notebook. Okay, so again, one-way analysis of variance, it's a hypothesis test, and similar to the two-sample t-test, it actually tests the equality of the means between samples, except the difference now is that we don't have two samples, but we have two or more samples, and typically we say we have k samples. Okay, so each sample has a certain sample size, NE. Okay, so that's the main difference between the two-sample t-test and the analysis, the one-way analysis of variance, each that it tests for the equality of the mean of two or more samples. Okay, and so just like with, it's a parametric test, so just like with the two-sample t-test, we make some assumptions, and the most important one is that the samples are drawn from a normal distribution, so from a population that has a normal distribution. The samples are drawn from populations with equal variance, right? So again, we're actually testing in this case whether all the k samples that we draw, whether they are all drawn from the same population or not, right? Because we assume this equal variance. And again, the sample should be drawn independently. Okay, so this is the claim we make. We have two hypotheses. The null hypothesis states that the means are indeed equal, and then we have the two-tailed alternative hypothesis, which states that they are not equal, which means that one of them is not equal, or two of them we don't know. We just know that they are not equal. So before we go on to explain how the test works, I'd like to first compare the two-sample t-test with the one-way analysis of variance, let's call it ANOVA, in case we indeed only have two samples. Okay, so that's what I'm showing here in this part of the code. So we have sample size 9, so we have two samples, gene A, gene B, and they are drawn from two normal populations. Okay, and these populations have a different mean. Yes, so we should reject the null hypothesis. Okay, and so we can compute the t-test p-value and the t-statistic, and we can also do that for ANOVA. So we also have a function in Python to do this one-way ANOVA, where again we just provide our two samples. So let's run this code. And so what we see for the the two-sample t-test, here we have the t-statistic, right? And so we have the corresponding p-value when we look that up in the null distribution. Okay, and so we can see here that we have a very nice low p-value as expected. Okay, if we look at the result of the ANOVA test, so we have a different value for the statistic. That's because ANOVA doesn't use the t-statistic, it uses an f-statistic, as I will explain in a minute. But it does show the same p-value, right? So this is exactly the same p-value, with some rounding errors here, but trust me, this is exactly the same p-value, which means that indeed they end up with the same conclusions, which is normal because they're testing the same claim here. Okay, so the f-statistic that is applied by the ANOVA test is simply just a ratio of two variances. And so in a minute we're going to look at these two variances, right? But before we do that, let's design a data set suitable for the explanation. So what we have is we have a certain treatment, okay, and we want to test the effect of this treatment on the expression level of, or we have several treatments, and we want to evaluate the effect of this treatment on the expression level of a specific gene. Okay, let's say we have three treatments. Treatment 1, treatment 2, treatment 3, which we want to compare, and we also have some control where we don't apply any of the treatments. So we have four groups, we have four samples that we're comparing. Okay, so let's say that each of those groups contains, or each of those samples contains 12 observations. So the sample size is equal for each of the samples, and it's equal to 12. Okay, so what we're going to do now is we're going to assume that we know the population from which, or populations from which the samples were drawn. So in this case, we're going to simulate that there is no difference between the means. So we have 4 samples, as you can see here, the control, the T1, T2, T3, and they're all drawn from the same population, as you can see here. Okay. So now, when in ANOVA, when we talk about these groups and these samples, we don't really talk about that, but we refer to the difference between the samples as a factor. So in our case, it's the treatment that is the factor. So we have 4 levels of treatment, 4 levels or groups, as we call them. So these would in this case be control, T1, T2, and T3. So what we will do now is concatenate these 4 samples into one data set, which is basically what I'm doing here. I'm making use of the pandas library to create a nice matrix style data frame, and it will be more clear if I actually execute this code and print this data frame. Okay, so that's the result. So this typically in ANOVA, this is the way we represent the data. Where we have a factor in a column, right? So we have here an observation, we have the actual gene expression level, okay? And then we also know to which group or to which level, as we defined here, this particular observation belongs to. So since we had like 12 observations in each of the samples, we will just a minute, okay? So we will have 12 controls, and we will have 12 observations for treatment T1, 12 for T2, and 12 for T3, right? So now what we're going to do next is we're going to plot these. So we don't see much in these data frames, but we will see much more when we actually plot this data. Okay, and so that's what we're getting. So here what I'm showing you is the distribution of all the values. So all the expression values, not taking into account to which level they belong to. Okay. And so here I plot the same expression values, but I split them up by the level, right? So I had 4 levels: control, T1, T2, and T3. Okay. So in the plot, the green triangle that you see is actually the mean value, right? Remember that this horizontal line is the median, so the green triangle is the mean. So let's take a look at the F statistic now. Okay, so again, what we're testing is whether there is a difference, or whether all these means that we see here, right? So for the different levels that we see for our factor, we see these we can see that they differ, but the question is, of course, is this difference that we see significant? Okay, so that's what we're going to test with this F statistic. So as I explained, the F statistic is simply the ratio of 2 variances. So we're now going to take a look at these 2 variances. Okay, so the first variance is basically looking at how variable or how different are these mean here. So it's the variance of these mean values. In this case, we have 4 of them. Okay, so that's basically what we see here. We call this the sum of squares of the treatment, or the treatment sum of squares, right? And it is known as the between group variation. Right. So it's the variation between the different groups, between the different levels, looking at the mean. So it's the variation of the mean between the different levels, okay? Also known as the explained variance, because it is actually the variance that we see here. So this is not taking the factor into account. Here it is, right? So the variance that we see between these levels of the factor is actually explained by the factor. That's why it's also referred to as explained variance. Okay. And so this first variance, the sum of squares of treatment, is defined as we see here, which is simply, if we look at the picture here, so the mean of the total, that would be this green triangle. So this would be the mean of all the expression values. Okay. And then we're going to run over the k levels. So we had 4 of them. So for each of them, we're going to look at the difference between this triangle, right, the total mean, and the mean for each of the levels individually. Okay, So we take the difference, we square that, we multiply by the sample size, because there is some weighting taking place here. Some of these groups might have much more samples, much more observations than other ones. Okay, and so that's what this is computing. So again, this is basically looking at how do these means deviate from the total mean if we don't take the factor into account, or when we don't take the factor into account. Okay, so we can compute that. That's what this small function here does. So this is basically an implementation of what we see here. Okay, and then we can take our 4 samples as we see here, and we can compute the treatment sum of squares. We can see that's this value here. So that's our first variance that we're going to use for the ratio. The second variance that we will use in the F statistic is known as the within group variation. So we have the between group variation, and this is the within group variation, also known as the unexplained variation. Right? And so before we go to this formula here, let's take a look here. So in this case, we're going to look at the variation of each of these individual levels. Right? So before we looked at the variation between the means, now we're going to look at the variation within each of these levels, right? And that is of course the unexplained variation, because there is no factor explaining why this is happening, that there is variation within the level. Okay, and so if you look at the formula here, which is known as the sum of squares of the error, right, that is basically what we're doing. So we're running again over the levels, and in each level we're going to look at the variation of the observation. So we're going to compare those to the mean expression level in that level. So that would be compared to the mean, to these green triangles that we have here. Okay, and so here again we have the function to compute this standard, the sum of squares of the error, right? So when we do that, we get this value here. Okay, and so what's very important to realize is that actually what we've been doing is that we have been dividing or partitioning this variance that we see here, so the variance of all the expression values, right? And we decompose that or partition that in some part that is due to the factor, right? So that would be the treatment sum of squares, and some unknown, unexplained variation, so that would be the within group variation or the sum of squares of the errors, right? And so if we look at the total variation, that is what we see here, the total sum of squares. So again, we go for each group, we look at the difference between the observation and the mean of all the expressions. So that would be this here, which would basically be just the variance of the expression values that we have here. Okay, and then if we compute that, so we can again implement this formula here. That's what we have done here. And then I can compute this total sum of squares, and if I'm correct, what I just explained, then this should equal to the sum of what we computed for the sum of squares of the treatment and the sum of squares of the error. So let's do that, and indeed we can see that we actually partitioned the variance that we observe for all the expression levels into a component that is explained by the factor and an unexplained component, which is the within group variability. So the F statistic now is the ratio of this sum of squares of the treatment over the sum of squares of the error. So these are our two variances in the F statistic. Okay, and so basically that means that we are dividing the explained variance over the unexplained variance, or the between group variability over the within group variability. And so since if we look at explained variance, so that would be part of this variance explained by the factor, by the 4 levels. So that would be the difference or the variance of these 4 means, these 4 green triangles. If that becomes bigger, a bigger part, then we can conclude that there is probably an effect of the drug. So if that becomes smaller and smaller, then we can start to conclude that there is no effect of the drug. Okay, and so this F statistic Okay, it is known that this F statistic under the null hypothesis, so in case that the means are indeed equal, then the F statistic follows an F distribution, so no more students T distribution, but in this case an F distribution which has two types of domains of freedom, degrees of freedom, I apologize. So the first one is based on the number of levels, the number of groups, so in our case that would be 4, and the second one is based on the total number of observations. So since we have 4 groups with 12 observations, that would be 48. Okay, and in this case also on the groups. So when we test this F statistic, we want to compute the p-value to compare it with the significance level. We need to choose the F distribution that corresponds to these degrees of freedom. So here you can see an example of that. So here we have different F distributions corresponding to different values of these two degrees of freedom, as you can see here. And I think it's very clear that the shape of these F distributions clearly differ between different values here, and it's very important to select the correct F distribution to compare your F statistic against. So now we can compute the F statistic for our data set. So we had 4 groups, we had 12 samples in each group, so the total number of observations is in n here. If we then use this formula here to compute the F statistic, we get this value, right? And so we have to compare that against the correct F distribution. So can do that here with this nice tool that you can see here from these nice people here. So what we need to specify is these 2 degrees of freedom. So in our case we had case 4, so -1 would be 3. So putting 3 in here to select the appropriate F distribution. And here we had 48 minus 4, so that would be 44. Okay, so when we do that, now we can see the F distribution that we're going to use, so that the one that corresponds to these 2 values for the degrees of freedom. Here we have to specify our F statistic, so let's do that. So that would be this value here. Okay, let's copy that, put that in here. Okay, and then what we see here is this value plotted somewhere here. So again, we had about 0.35, so that would be here. Okay, and so now the probability of observing this value or a more extreme value is shown by the orange or the pink area that you can see here, right? And normally, just a minute, yeah, so we get a p-value, so the area under the curve, so under this part of the curve, is 0.787, so that's quite a high p-value, which is normal because of course we sampled our 4 samples from the same distribution, from the same population. Let's go back, as we can see here. Okay, so we were expecting to accept the null hypothesis. And so now if we use our 4 samples, or our one data set with a factor with 4 levels, and we compute, we use the Python function to compute the ANOVA test. What we can see here is that indeed the F statistic has the same value that what we computed, and if you look at the p-value, that actually corresponds very well with what we found in the tool that I just shown you. Okay, so in ANOVA it is more appropriate to have more detailed information about the test, and so there's another way to do this test as I'm showing you here. So this would be part of the stats models module, and so when we perform the test with this function, we get slightly more information. So we can see here that we have our factor, right, and here is what's left. So this would be the sum of squares of the treatment. Okay, this would be the sum of squares of the errors, from which we are going to compute the F statistic, as what is done here. So that's the ratio of those two. We have the domains of freedoms as specified here, and from that we can then compute the p-value as is shown here. So now let's change the data set a little bit, right? So now we're going to sample again we have one factor with 4 levels, as you can see here, but now in one of those levels, right, the observations are actually drawn from a population with a different mean. Okay, so in this case we should conclude that the means are not equal. Okay, so let's first of all plot this. So now we get this situation, right, where we can see that one of them has a little bit of a different mean, but again, I mean, we need to compute the significance of these differences, because even when the means would have been equal, we would still not observe them as being equal. So we should still check whether these differences that we see are indeed significant. Okay, and so we can use our Python function to do that, to compute this table. Right, and so we can have all the information we need. We have a much higher value for the F statistic, and we have seen that that brings us into the tail. So that means lower, smaller areas under the curve. And as you can see here, a very small area under the curve, with which produces a very low p-value, which means we should reject the null hypothesis, which is correct because we indeed have one of the levels drawn from a population with a different mean. So now we have our factor treatment with 4 levels, and we want to know whether the mean gene expression is equal in each of those levels. And as such, we are actually verifying whether a certain drug has any impact on the expression level of the gene. Now, there could of course be more factors that have an influence on the expression level of this gene, and let's consider the sex could be one of them. Whether you're a male or a female, that you could have different expression levels just because of that factor as well, right? And so in two-way ANOVA, we are actually going to show how to take these 2 factors into account, and also why it is important when you know that there are multiple factors that can influence your variable, to actually use them in an ANOVA model. So in this case we will consider 2 factors, but of course you can extend that to more factors than that. Okay, so let's consider the data set that we constructed here. So we had 12 observations in each of our levels, and so we had 4 levels, and we made one of these levels having a different mean. So they were drawn from a population with a different mean. You can see that here. And what we're going to do now is we're going to add a factor to that data set. That's what I'm doing here. So I have a factor called 6, and I'm just randomly assigning male or a female or male to each of the observations, which is what I'm doing here. And then I'm going to create this data frame so that it contains this new column that we created for this 6 factor. Okay, and so let's create this data set. If we print it, you can see this. So basically, just a minute. So we added this column here. So we have the observations, we have the treatment factor, and now we have this factor 6, and we have of course our expression level of the gene. Okay, and so you can see that we now have nicely 6 males and 6 females in each of our levels, in each of the treatment levels. Okay, so now we can plot this data set. Okay, that's what I'm doing here. And we get this picture here. So what we have now is we had our the plot that showed all the observations. So we had this the total sum of squares that we were looking at here. Okay, and then we have this plot where we split it up the variance here into 4 levels, right? So with factor treatment. Okay, now of course we also have our factor 6, so we can make the same a plot for 6, where we here only plot the females and here only plot the males. Okay, and then we can have this plot as well, where we plot both factors, right? So you can see now that we have treatment here, right? And for each of the treatment we also split this up into male or female. Okay, so now let's first perform a one-way ANOVA, and we're going to perform it on the factor treatment. Okay, so if we execute this code here, okay, we know that there was clear difference here in mean for treatment 2, and we can also see that reflected in a very low p-value, as you can see here. Okay, so obviously at this significance level we actually reject the null hypothesis, and we do that correctly. So if we can do the same thing for factor 6, right? So we do a one-way ANOVA to check for factor 6, and what you obviously expected is that we get very high p-value because we just randomly assign male female to the observations. Okay, and so that brings us to two-way ANOVA, where instead of having just one of the sum of squares for the treatment, we now have two sum of squares for treatment and treatment and for 6, for factor 6 and for factor treatment. And of course we also still have this unexplained part, right? And so what this tells us here, just like with the one-way ANOVA, that the total variance, like I explained, what we have here is now split up in a part that is explained by the treatment and a part that is explained by the factor 6, and then an unexplained part, right? So the sum of squares of the errors, right? And so we have the part here explained by the treatment, a part here explained by the 6, and then what is actually left, the sum of squares of the errors, is the variation that we still observe when we partition the whole variance based on both factors, which is what we've been doing here, but there is still variation in here, okay? And so that is what's left. It's unexplained, it's not explained by both factors, and so that would be the sum of squares of the errors that we get there, okay? So let's perform a two-way ANOVA. So quite similar here, we just have to add another treatment here. So we're saying that the expression level is actually a function of treatment plus 6. Okay, and so what we can see, we are indeed still rejecting the null hypothesis for factor treatment, and we're still accepting the null hypothesis for the factor 6. Okay. So now let's make a drastic change in this data set, right? So instead of randomly assigning male and female, as we just did, we're now going to also add a small value. So we have a very consistent 0.05 value. We're going to add that to the expression level of males, right? So males, if you're a male, the gene expression level is typically higher, right? It's about 0.05 higher. Let's say it is. So let's create that data set. Okay, now we can plot that data set again. That's what I'm doing here. Okay, so here we have again all the observations. This is all the variance that we observe, and here we have split this up based on our two factors, right? And you can see that because of course we added a significant number to the expression level for males, you can clearly see here that there is also an effect or an impact of the factor 6 on the expression level. Okay, that's a very significant impact, as you can see here. Okay, so now what we can do is again act as if we don't know about this factor 6, right? So let's plot that here. Okay, so now this would be just one-way ANOVA. We don't know about the effect of factor 6 on the expression level, but of course it is there, so we get this situation here. Okay, and if we then do the one-way ANOVA, now what you can see now, even though we know that there is a treatment effect, so that the means aren't equal because we have a different withdrawn from a different population for treatment 2, even when we know that, we can still see that the p-value indicates that we should accept the null hypothesis and we should not reject the null hypothesis. Okay, and so that's what's important here, that if we don't take this factor 6 into account, we end up making the wrong conclusions, right? Because factor 6 also has a big impact on the expression level of our gene. Okay, and so if we plot, so we act that we only know about 6, so that's the situation here, and so clearly this should show a very big difference in mean, as is indicated by this very small p-value. Okay, And so now what we're going to do is we're going to do the two-way ANOVA, right? So up till now we have only rejected the null hypothesis for our factor 6, but now we're going to partition the total variance based on both the factors, treatment and sex, right? And so we're going to do the two-way ANOVA. And so now what you can see here, and that's again very important, that we now have two very small p-values. In fact, the p-value for treatment has become very, very small, as expected. And so the reason for that is that we will have now a smaller sum of square of the error, because we partitioned the total sum of squares based on both factors. So this is the formula. What you can see here is that we run over each of the partitions, and so I can show you that here again. So basically the sum of square of the errors is what's still left after partitioning this variance based on both factors. So that would be the variance that we see here plus the variance that we see here plus this one 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 plus this one, right? So that is basically what this formula is telling us here. And so if we compare them again, right, so this will be the one-way ANOVA on the treatment, right? So where we got this p-value that was much larger than the significance level. Okay, and when we added the factor 6, I took that into account, then we had this much smaller p-value, which is definitely much lower than the significance level. But you can also see here that here we have this sum of square of the errors, which has been significantly reduced here, right? And so remember that the F statistic is the ratio of these things, so smaller sum of square of the errors will mean a bigger F statistic, and that will mean a smaller p-value. Next to adding factors to the analysis, we can also look at interaction between factors. And so an example of such an interaction is that suppose we have two factors, again treatment, and this case treatment has two levels, T1 and T2, and that we again have a factor 6 with again two levels, male and female. But this time it is in treatment 1, the expression level of our gene is higher for males than for females. And when we apply treatment 2, in general what we see is that the expression level is lower for males than for females, right? So there is an interaction between those two factors. Okay. So first let's look at our data set that we've been looking at so far. So we had an effect of both sex and treatment, as I've shown here. So let's look at interaction as well. We can formulate that like this. So now we are looking, maybe should explain this first. So what we're now doing is we're partitioning the total variance, the total sum of squares, I'm sorry, we're partitioning it by our two factors, but we also have a part explained by an interaction between these two treatments. Okay, so we just added that to our analysis. And so if we do this two-way ANOVA taking into account the interaction, so this is just considered another factor here. Okay, so then we can see that indeed we still have our two factors here, treatment and sex, showing a very low p-value, while our treatment, interaction that we've been looking at here doesn't show a p-value that is low enough, or that is lower than the significance level that we defined here. Right? So we conclude that there is no interaction here between the treatment and sex, which is also the case because we did not add that interaction. So let's create a different data set where we add such an interaction. So what I'm doing here is I have, like I can just explain, I have a factor treatment which is two levels, T1 and T2, okay? And for each of them I have males and females, okay? And so in T1 the males are drawn from a population with a mean of 0.26, okay? The females are drawn from a population with a mean of 0.28, okay? So we can see that in this case females typically have a higher expression level than males. So for the treatment 2, what I'm doing here is I'm sampling or drawing from a population that has a mean of 0.3 for males and 0.26 for females. So in this case, males have higher expression level. Okay, but of course it's very clear that for all the combinations here, we have very different population means. Okay, maybe not this one. So let's create this data set and plot it. So I've plotted it two ways now. So what I'm doing first here, so it's the same data, but here I just plot treatment on this axis, right? And then I split these up by 6. And here I do the opposite. So I have here, I have factor 6, which I have male and female, and I split those up by treatment. So you can clearly see that they have differences in mean. Okay. So let's first consider one-way ANOVA. So we consider each of the factors individually. So we look at the treatment individually and we look at the sex individually. We don't take the interaction into account. We plot the ANOVA table. Okay, now we can see here that, okay, this is higher than the significance level, so we accept the null hypothesis. Same here, it's close, but it's still higher than the significance level, so we accept the null hypothesis. Okay, so even though there are very clear differences, right, between these factors, okay, between the levels of the factors, right, and even though there is an interaction, we don't see any of that if we just perform one-way ANOVA. Okay. Now, if we do take everything into account, no, let's just first do the two-way ANOVA without taking the interaction into account. So that's what I'm doing here. So now I took into account that we have two factors, right? But not the fact that we are also looking at an interaction between these two factors. And again, what we can see is that both of them accept the null hypothesis, even though they should reject the null hypothesis, right? And clearly they should. Okay. So finally, let's add the interaction factor. Let's say that there might be one. Let's consider one. And then that changes the picture drastically. So now all of our factors, so including the interaction, are actually rejecting the null hypothesis, right? So they show differences in mean, which is indeed correct, right? And to stress, to show you why this is, so what I'm plotting here is the data individually, looking at each of the factors individually, right? So if I would just split up by treatment, right, not taking into account 6, then you can see that indeed this doesn't really show a significant difference in mean, and the statistics also tell us that this is the case. And the same thing for 6, right? Even though it was close, the statistics told us that there was no difference in mean here, and only when we took into account both factors and the interaction, we were able to conclude that indeed there is a big effect both of treatment and of 6, and there is an interaction between these two as well. So that brings us to power analysis, where everything comes together. So we are actually already touched power analysis. So we define it as the probability of correctly rejecting a false null hypothesis, right? And so sometimes it's also written as 1 minus beta, where beta is the probability of accepting a false null hypothesis. Okay. Now, so when you design an experiment, so for instance, you want to know whether the expression level of two genes A and B differ. So you want to know whether the mean expression level of those two genes differ. Okay. And so basically you're asked to design an experiment, and one question that you need to answer there is, how many observations do I need, right? So what is the sample size that I need? Is a small sample size enough? Do I need a big sample size? And so that's the question we're going to try to answer here using power analysis, right? So that's what I'm stating here. So before you actually start an experiment, it's very good practice to estimate the sample size required to find an effect of interest. So if it exists, of course. So what that means, for instance, in our case of gene expression levels between gene A and gene B, we might say that we want to at least find a minimum difference in the mean expression level of 0.02. So 0.02 or higher. That's the minimum we want to be able to detect. So we want to design a statistical experiment that, if there exists a difference between gene A and gene B, so a mean expression level difference between those two genes of 0.02 or higher, then we want to be able to detect that, so to be able to call that significant, that difference. Okay, and so the question we're asking ourselves is, how many samples do I need to do that? Okay, and so we already seen that the power of the two-sample t-test is of course influenced by the variance of the populations from which the samples were drawn. Okay, and we did this experiment, and I'm repeating this experiment shortly here. So what we're doing is we're going to, for different variances of the population from which we will draw the sample, right? So that's what we're doing here. We have gene A, we have gene B. We're drawing these from normal populations, okay? And the populations have this variance, the standard deviation, which I arranged over here. Okay, I also made sure that there is a difference between my two populations. Okay, so the difference is my effect size. That's what I define here, which is 0.02. So that's the minimum effect size I wanted to detect. Okay, and so we have also a fixed sample size, and we also have a fixed significance level here. Okay, and so we're going for each of those populations that we have here, we're going to repeatedly sample two samples for gene A and for gene B. Now we're going to do the two-sample t-test. Okay, that's what we're doing here. And then to compute the power, we're going to look at what is the probability of correctly rejecting, right? So what is the probability, or how many times do I see my p-value being smaller than my significance level alpha? Okay, and that will compute me the power. Okay, so if I execute that, you can see, and we already saw that for a increasing variance of the population, we see of course a decreasing power. Okay, so the smaller the variance, the higher the power. Okay. And so we did a similar experiment where we fixed the variance of the population. So let's say it's a standard deviation of 0.01, but now we range over sample sizes. So we now have different sample sizes. So we have the same experiment, but instead of fixing the sample size and varying the population variance or standard deviation, we will now fix the variance, and we will consider different values for the sample size. Okay, so again, notice here we still have a difference between the two populations. So I execute this, and of course, as we have already seen, the larger the sample size, the bigger the power of our two-sample t-test. Okay, and now we can add to that, of course, we can now fix both sample size and variance, but we're now going to vary the effect size, right? So we're going to vary that from a very small effect size. We want to see a very small difference and be able to call it significant. And we're going to go up to a much bigger effect size, right? So a much clearer difference between the two sample means. Okay, everything else we can fix. If we do that, of course, as expected, when we increase the effect size, it becomes easier, so more apparent, and of course the power of our test significantly increases. Okay, and so what's important to notice here is that the power of a hypothesis test, right, depends on these four numbers. So we have the effect size, I've shown you that. We have the population variance, I've shown you that. We have the sample size, I've shown you that. And of course, we also have the significance levels, which actually determines how to compute the power. Okay. So now we can actually fix the power, we can fix the effect size, we can fix the population variance. Hopefully we get some estimate of the population variance, because again we don't know the population. And we can fix the significance level, and from that we can actually compute the sample size. So we can give values to each of those four, and from that we can compute the sample size required to obtain those values. So to obtain this power and to actually get the minimum effect size that we want. Yes, and so in Python we have this function here that is able to compute the sample size from these fixed values that we set here. Okay, and so what we're going to do here is, instead of ranging the effect size or the sample size or the variance of the population, we're going to range the power now. So we're going to check what is the sample size required to get a 99% power or a 95% power. Oops. or a 90% or an 80% power. Okay, and so we're going to compute for each of these powers what is the sample size required given fixed values for, so we have a fixed value for the variance, we have a fixed value for the effect size, and we also have these fixed values for our significance level. Okay. So what this is showing us is that, as you can see here, suppose we want to have a power of 95%, right? So high enough. Keep in mind, there's still 5% chance that we don't, that we are unlucky, that even though there is some effect that we don't see it. And so in order to get that, we would need at least 11 observations, right? Okay. And so basically we can check whether this is indeed the case, so we can again simulate. So let's say n is indeed 11, so that's our sample size, okay? And we're going to compute the power that we obtain for this sample size, right? So we're going to again 1,000 times repeat a two-way t-test, a two-sample t-test, okay? And so we still have this effect size, we still have this fixed variance, okay? And so for each of those iterations, we're going to compute how many times we can see a p-value smaller than the significance level in order to obtain the power, given that we have a sample size equal to 11. So we can execute that, and we can see that that is indeed very close to our, it's a bit lower, but it's very close to 95%. Okay. So there's two things here. So first of all, in order to compute the sample size required to obtain a certain power, to see a certain effect size, one needs to have some estimate of the variance of the population from which the samples are drawn, right? Which is sometimes very hard to do. Hopefully you can find some information on that in the scientific literature, or typically one designs a pilot experiment with small sample size and try to estimate the variance of the population from that small sample size, and then use that to determine how many more samples are required to obtain the desired power of the test. And second, of course, it makes sense that you want to use as many samples, as many observations as possible. So you want to have a big sample size, because as I've shown you, that increases the power of your test significantly. You can detect much smaller effect sizes, right? But of course, there is this big trade-off, because samples can be expensive. It takes time to collect samples. It's sometimes also very hard to find the samples for rare diseases, for instance. And so there is some sort of trade-off between the power of, in this case, our two-sample t-test and the sample size required to actually observe a certain effect size, right? So what I'm going to do is I'm going to compute the power of our two-sample t-test for different sample sizes. So that's what I'm going to run here. So you can see here the power for sample size 2 is quite small, and of course it increases as the sample size increases as well. Now let's get a better view of what I'm plotting here. So let's plot this using this function here. So this is the same information, okay? So we have the sample size here, increasing sample size, and here of course increasing power. And so what's important to notice here is that in the beginning, for very small sample sizes, adding one more observation actually significantly increases the power of your test, right? So here there's big gains to make in power by adding just a few more observations. Well, at some point you can see some plateauing here, right? So at this point your power of your test isn't going to increase anymore, okay? But of course you're still spending time and money on adding more samples. So in order to get some idea of how many samples you would at least require for certain power, a plot like this brings a lot of information. When we then look at statistics in biomedical research, we can immediately see why this power analysis is actually important. So if you look at statistics in biomedical research, first of all, we are restricted to very small sample sizes. So we have this time and money considerations, but also the fact that it's not always easy to find representative patients. Okay. Second, to make this even a bigger problem, there is an enormous biological variability, right? So typically, if you, for instance, look at gene or protein expressions, there are many factors that can influence this gene and protein expression, which is, by the way, also why people tend to resort to model organisms. So, for instance, mouse models that were tried to make these mouse models as similar as possible, but thereby, of course, reducing this biological variability. And we have seen that low variance in the population has a very drastic effect on the power of our analysis. Okay. And to make things even worse, we also have technical variability, so induced by sample preparation. So there's variability induced by different differences in the sample preparation, but also in the measurement machines, right? So we have kind of noisy measurements. If you look at microarrays, mass spec machines, they have their imprecisions, right? So they induce technical variability as well. Right? And then also we have the fact that we cannot control for all the relevant variables. So we have looked at the sex, right? So male, female can have an impact, smoking, non-smoking, things like that. So, but it's impossible to control for all of these relevant variables, right? And then on top of that, in biomedical research, we are also typically interested in very small effects, or very small differences in expression of genes or proteins. So that actually makes biomedical research a very good fit for statistics. I'd like to end with a story that shows how things can go terribly wrong when you ignore the fact that you need to make some assumptions to do tests. In our case, for instance, in the hypothesis tests, one of the assumptions was that the observations were drawn independently, right? So that the samples were drawn independently. One example here, of course, is that if you start using twins, for instance, in an experiment, and you look at some gene expression or protein expression, there is some dependence between these two observations. You know, one might assume that they have much more in common than the other observations have between them. So that would be one clear example of a dependence between your observations. And so this story is a story of Sally Clark. So several years ago it was in the news. You can find it also on the wiki. So Sally also she had her first son died in 1996, which was a few weeks after the birth, and then also she got a second son that also died in very similar circumstances. So that would be 2 years later, right? And so what happens is that Sally Clark was actually arrested and tried for both deaths. So she was found guilty of murder, these things. Right. And so the defense argued that the children had died of sudden infant death syndrome, but actually the trial decided differently about that. So what they said is that for a non-smoking family like the Clarks, the probability of a single cot death was estimated as 1 in 8,543. Right. So the probability of 2 in the same family was around 1 in 73 million. Right. So given that there are around 700,000 live births in Britain every year, double cut death would be expected to occur once every 100 years. And so based on that, she was trialed and found guilty. So luckily there are some statistical institutions that look into this, right? And so they actually wrote a report on this. So the calculation was based on the assumption that the two deaths in the same family are independent, right? So that's why they multiplied the numbers as I'm showing. So that's why they multiplied the numbers here, right? By the assumption that they are independent. Okay, so the RSS argued that there are very strong reasons for supposing that that assumption is actually false, right? There may well be unknown genetic or environmental factors. So first of all, that predispose families to SIDS, so that a second case within the same family becomes much more likely, right? And so they went investigated that. Well, just a minute, they went investigating that. So they wrote a whole report on a study in which they looked at an extensive SIDS statistics data in the whole history of England. right? And so they concluded that after the first cut death, so based on the study here, after the first cut death, the chances of a second become greatly increased, so by a dependency factor of 5 to 10, which is significant, right? So that means that there is clearly a dependence, and that the reason why Sally was found guilty is completely wrong, but is based on the fact that you ignore the dependence between those two observations, right? And it's actually even worse than that. So even the 1 in 73 million figure, even if that were valid, right? So it's not 73 million, but suppose it would be 1 in 73 million. So they should not have interpreted that as a probability of Clark's innocence, right? So that's important. So that's actually that's not what the p-value means, right? Because that's basically what they computed, but the p-value doesn't tell you the probability that your null hypothesis is correct, right? That's not what it's doing. Okay. And then there's the fact that so they consider murder as an alternative explanation for the deaths, but there could be other alternative explanations which were not investigated. And finally, and I think that's also a very good point, is that although double slits are very rare, okay, double infant murder is likely to be even rarer, right? So the probability of Clark's innocence was actually quite high if you follow the same reasoning as they did for the double slits, and they would do that for the double infant murder, then it would be obvious that the innocence was very high.